Hello and welcome to another one of these ADD videos. Today we're going to be looking at the concept of electrophilic additions and Markonikov's rule. So basically the whole chapter deals with the addition to a double bond. So if you look at a double bond, the pi electrons make it electron rich, and it's an excellent candidate for the binding of an electrophile. Electrophiles, if you remember, love electrons, so they are electron poor. And basically, whenever this electron poor species binds to the double bond, it creates a carbocation, and this concept is called electrophilic addition to an alkene. Okay, so Markonikov's rule, if we're looking at just HBr at first, that's what they use to discover the rule. The addition of the proton acid, and if you look at the acid, let's look at HBr real quick. Quick side note. If you remember, the electronegativity of bromine is really high in comparison to hydrogen. So therefore, hydrogen is dying for electrons. It's got a partial positive charge. Bromine's hogging all the electrons. What's up with that, bromine? And basically it's electrophilic in nature now, and it's going to add to an alkene double bond, and it's always going to add in such a way to give the most stable carbocation. So the original way the rule was stated was it binds to the carbon with the most protons. Okay, that way whenever you form the plus charge on the other carbon that you didn't bind to, it has the most carbons on it. So if you remember the inductive effect, that's the sharing of the burden of that positive charge, and the more carbons you have attached to the carbon with the cation charge, the plus charge, then the more stable it is. So that's the hierarchy of that. So let's look at this example here. Here we have two choices. One, we have a choice in which HBr, the H binds to this carbon here, in which it had 2 hydrogens, or it binds to this carbon where there were no hydrogens attached to that carbon right here. Right, these are both methyl groups here. If you can't see, let's go back over there. So the first scenario, if I bind to the carbon 2 here, then what happens is I get a 1,2 tertiary carbocation, which is very stable. Whereas if I bind to this carbon here, the resulting carbocation is on the other carbon, and that is a primary carbocation, not as stable. So between the two, this path will never happen. Okay, it's this one up here, the tertiary path, which I kind of wrote through there, sorry. But you can always rewind if you need to see it again. So once we have that HBr, right, is what we had, and the H bound right there, and create this tertiary carbocation, well, the Br is still hanging around going, what do I do now? I've got an extra electron, I don't like this many electrons. Oh, you need an electron carbon? Let's form a bond. They form a bond. I know that was a little corny, I apologize. But this is always the product that would occur given those circumstances. And that concept there, when you have a certain product that's always preferred when you have a possible two products, is called regioselected. Okay, and that's basically Markonikov's rule. The electrophile binds to the one that has the most hydrogens, is the extended version of the rule. So if we bind something besides HBr, the rule states that such in a manner that the electrophile binds to the least substituted carbon atom. Why? So we can create the most stable carbocation. And it holds true for all of the electrophilic additions that you're going to study, except for hydroboration and free radical addition of HBr. They use peroxides to make free radicals, and these two will exhibit the anti-Markonikov orientation. That's a whole different video. This is just a concept video. I'll do some examples of each one of these different Markonikov reactions. So make sure you check those out. I hope I've clarified it. If you can think big picture, you won't get lost in the details, right? So try to see everything from a step back, and then try to understand the subtle nuances between the individual reactions. I hope I've clarified things. Practice, practice, practice. Thank you, and have a nice day.